Swayam Prabha. Digital India. Educated India.
Namaskara, welcome back to real time digital signal processing course. So, we will discuss today correlation. To recap, in the last class we have covered about overlap save method. Both the overlap previous to that we had covered overlap add method for continuous input signal, how we can calculate our FFT, and then we had seen lab also. Coming to in today's class we will discuss about correlation. So, what is the definition of correlation, or why do we need it? We will look at it. So, basically a process of comparing two data sequences to obtain a measure of similarity between them. So, most of you must be knowing that you will be trying to correlate one person with other, either in terms of their habits or their look or their appearance. That is what you will be looking at. In this case we will be looking with our signals, whatever we are going to get the thing. So, one of it is in the application of voice recognition in audio signal processing. So, which requires comparison of different speech waveforms. So, you are want to recognize somebody's voice, okay, and then you have stored originally and then marked it, this is the original person's voice, and some other people their voice is recorded or from the same person. Then you want to see that whether whatever stored is going to match with that particular person's voice. So, this is one of the application we need the correlation. Next, in the case of image classification in image processing, which requires comparison of different image data. As I was telling, so you might have taken the image somewhere else and then you want to have a see that the current image whether there is any correlation or not. So, the other application, one of the mostly used, what we will call it in day to day life, is object detection and location in basically sonar and radar systems. So, which require comparison of the transmitted signal and the signal reflected from the target objects. So, it you want to all of you know now drone is becoming mostly popular. So, if you want to identify if one of the drone is going to cross our border or whatever may be the thing. So, you want to identify it as a foe and then you want to destroy it. So, a lot of work is happening. The same way in the sonar area is one of the sea area. So, submarines and other things. So, they will be reflecting through signals through radars basically, and then the reflected wave which comes back you have to process it and then see that what correlation it has with the template what we have it. And even you would be in case of aeroplanes basically. So, you want to see that what kind of aeroplane which is running, whether it is military or civil. So, that also reflection you will be catching through the radar and then you will be finding out. So, you know that correlation is used everywhere. So, the fundamental measure of similarity between the two sequences, we call it x of and y of n, is the sum of the products of the corresponding pairs of data values, that is sigma x of n into y of n, what we represent it. Then what we are going to say, so we say if the is it positively correlated when we are going to say this? If there is some kind of proportionality relationship between x of n and y of n with positive or negative values generally occurring concurrently in both sequences, then sum of the products will be a positive value, because even both of them are negative, we know that the product is going to give us positive, and both of them are positive, then it will be giving the positive value. So, then we will be saying that as a positive correlation. When we call that as negative, if there is some kind of inverse proportionality relationship between x of n and y of n with positive values in one sequence generally accompanied by negative values in the other sequence, then we know that sum of products will be a negative value, indicating that is negative correlation between the two sequences. So, when we say there is no correlation between the two sequences, if the two sequences are independent with positive values and negative values equally likely to occur in both, actually the sum of products will tend towards 0. So, we call it as due to self cancelling of the product terms in summation. So, then we say that they are not correlated. So, continuing with the thing, so we say if two sequences x of n and y of n, the cross correlation function, we call it as Cxy of p, is defined by this equation. What do we say? Cxy of p is equal to limit n tending to infinity 1 by n, small n is equal to 0 to n minus 1 x of n into n minus p. So, we say where plus or minus p represent the number of sampling points by which y of n has been delayed or advanced in time with respect to x of n, and 1 by n is included as a normalization scaling factor to ensure that the cross correlation of two periodic sequences converge to the same result as more and more sample pairs from two sequences are included in the cross correlation operation. So, that we are trying to avoid the overflow by scaling it. Okay. So, how do we define the autocorrelation? When y of n equal to x of n, we have a special case whereby the cross correlation function becomes the autocorrelation function. The equation is given by Cxx of p is equal to limit n tending to infinity, the same scaling factor 1 by n, n will be going from 0 to n minus 1, x of n into y of n minus p. In this case, the maximum autocorrelation where we are going to get is when p is equal to 0. Since two identical in phase signals are being compared and the autocorrelation value decreases as p is going to increase. So, we will see how we are going to calculate our correlation as an example. So, what we have it the same example for FFT, what we have taken the thing, here also we will be taking the same this thing x of n and then h of n. Here it is x of n is 2001 and h of n is given by 4321. So, now we will write compute our cross correlation by writing the table. So, n will be varying between -3, -2, -1, this is and then 0, 1 to 3 greater than equal to 7, we know that it is going to be 0, because we know that like linear convolution, we call it as linear correlation. Here the length is going to be r L plus m minus 1. So, that is what we needed, even the negative side. So, x of n we are going to write it as this thing. So, we know that in the negative region it is 0, and if nothing is mentioned, we assume the starts from 0. Sometimes if you want to say that it is starting from the negative side of it, so you may mark with an upper arrow here stating that this is our 0th location basically. So, it is 2001 and then elsewhere it is 0 what we have assumed P, okay. And then we will be computing our correlation equation, that is CXH, that is cross correlation with respect to P. So, first one is H of n plus 3, because P is equal to minus here basically minus 3, it is going to be n plus 3. So, it will be 4 3 2 1 what we assume the thing here, and then rest of them zeros. So, when you do the multiplication here, so what you are going to get is when P is equal to minus 3. So, you are doing the multiplication, 2 into 1 is 2, rest of them are zeros, and we have to scale it by n. Capital N is 4 because both the sequences are of length 4 in this case, by 4 is going to give us 0.5. So, same way what you have to do is next is n plus 2. So, you will be shifting H of n sequence right by one place, and then you will be computing your cross correlation here. Same way you do the thing when this thing x of n and h of n at 0, we will be seeing that that is P is equal to 0. So, both will be coinciding with each other, that is 2001 and 4321, and then you will be seeing that the correlation value at this is peak, it is 2.25. So, then you will be moving away from the thing, P is equal to you will be giving it as 1, 2 and then 3 and then 4. So, this is our output of linear cross correlation. So, what is the difference with respect to our convolution? So, here H of n is not folded in the correlation process. So, we fold H of n in the case of convolution, here it goes as it is not folded. That is the difference between our convolution and then correlation. So, coming with continuing with the correlation. So, what is it? It is often desirable in practice to make the autocorrelation function values independent of the signal scaling by normalizing the autocorrelation function with respect to its maximum value at 0 phase. So, that it need not have to depend on the thing. So, what is that? Normalization results in an autocorrelation coefficient, we call it as rho xx, whose values always lie in a fixed range of plus or minus 1. So, when we take the autocorrelation rho xx of p, it will be Cxx of p divided by Cxx of 0. So, similarly normalizing the cross correlation function results in cross correlation coefficient rho xy, which is given by rho xy of p is nothing but our Cxy of p divided by root of Cxx of 0 at the 0 autocorrelation value what you will be taking it here for one of the signal, and then autocorrelation this thing coefficient Cyy of the second signal. So, under square root you will be doing it, which will normalize our this thing cross correlation function. So, the note at this place is our rho xy lies in the fixed range of plus or minus 1 with plus 1, 0 and minus 1, indicating 100% positive correlation. When it is 0, it is no correlation, and 100% negative correlation respectively if it falls in this values. So, what does it say? That our cross correlation magnitude of it should be less than or equal to square root of this function basically. So, as an example, we will take the same sequence x of n and then h of n. We have already calculated their cross correlation coefficient. Now, we will see the values of it, that is autocorrelation Cxx of 0 is nothing but 1 by 4 into n is equal to 0 to 3 x of n squared what we will be doing it, which is nothing but 1 by 4 into 2 square plus 0 square plus 0 square plus 1 squared, which is equal to 1.25. And then autocorrelation of the H signal, that is we have it 0, it is equivalent to 1 by 4 into same way n is equal to 0 to 3 H of n squared. So, when you substitute these values you will be getting 7.5. Now, we have computed cross correlation CXH of P in the previous table, as you can see it 0.5, 1.5. So, how we can normalize this using this equation. So, what is the first value? What we have is 0.5 divided by square root of our 1.25 into 7.5 will give us the value 0.16. Same way for all the our autocorrelation values you can calculate or normalizing the thing will give these values which have been put into table. So, you can go and then compute for rest of them whether it is going to match or not. Fine. So, now just like our linear correlation and linear convolution, so we have the circular correlation equivalent to circular convolution. So, how we are going to write our circular correlation in this case? We call it as Cxy of P is nothing but 1 by n, n will be varying between 0 to n minus 1, x of n into y of n minus p. So, in this case p will also be varying between 0 to n minus 1. So, when we compute the circular this thing correlation between these two sequences as we had done it with linear correlation. So, what we have it x of n is now we have 2001 and h of n is given as 4321, and then the capital N in this case is 4. So, we will be going between 0 to 3, after that it is going to repeat. So, here when we calculate it, so this is nothing but 2 into 4 plus 0 into 3 plus 0 into 2 plus 1 into 1 and then scale by 4 what we are doing it capital N. Then you will be seeing that it is going to give us 2.25, the next one is 1 and then next one is 1.75 and then the last one in this case is going to be 2.5. Is something going to strike to you? So, you can see that what was our earlier case. So, it is 2.25 in the thing it is matching, and you will be seeing only one is going to match like a linear convolution. Here also circular convolution with linear convolution, there is only one value which is the at 0 which is going to match, rest of them are not going to match. So, to get again our linear correlation, how we are going to implement it? So, this is one of the questions. So, how did we do linear convolution from circular convolution? By padding zeros. Here also you can pad zeros and then compute linear correlation from the circular correlation. So, this is going to be your assignment or take home, I will call it as problem solving thing. So, you can work it out and then come back and then tell me whether you have got the results correctly or not. Okay. So, now we will see some of the DFT property of our circular correlation. Just we did it for the convolution, we will do it for correlation. So, what does it say? May be stated formally with this: if our Cxy of P is given by this equation, then we call it as correlation of xy r, we will put it, which is equivalent to 1 by n xr into yr conjugate. So, the multiplication is going to be xr with yr conjugate and then scaled by 1 by n. So, here we say Cxyr XR and YR are the DFTs of CXYP, and XN and YN are the inputs, and YR conjugate is the complex conjugate of our YR DFT of Y small y n basically. Fine. So, now we will see how we are going to compute our correlation output. So, just like we did for the DFT, so we will be using I will be putting it as DIF FFT. So, this is the butterfly structure what we have it. So, we have 1 by 4 is the here also, because the length of the sequence is 4 what we have taken the thing. So, 1 by n is 1 by 4 in this, and these are the points what we will be getting it in basically inverse of DFT basically. So, this is C0, C1 and A0, A1, B0 and B1, and then we will be getting out our x of 0, x of 2, x of 1 and x of 3. So, we have calculated our DFT of 2001 in the previous class. So, which gave us 2 plus j comma 1 comma 2 minus j are the DFT of this sequence. So, I think we have not calculated DFT of h of n. So, you can calculate in the same way using DIT FFT, that is decimation in time for fast Fourier transform butterfly structure, and compute the DFT of 4321. In this case, we have assumed that we have calculated previously and using the values what we have it. So, which gives us 10 comma 2 minus j2 comma 2 comma 2 plus j2. So, these are the DFT of 4321. Now, we will calculate the circular correlation CXYR what we have to calculate. So, 1 by n into we have to do XR into YR conjugate. So, if we substitute the thing, so this is our XR, okay, multiplication with YR, this is the one conjugate what we have to take the thing. So, how we are going to represent this? So, this is 10, 2 minus j2, 2 and then 2 plus j2. So, when you take the conjugate of this becomes positive and this becomes negative, and then calculate these values. So, you will be seeing that it is going to be 7.5, 0.5 plus j 1.5 and then 0.5, 0.5 minus j 1.5. So, this is our value for CXYR. Now, how we will be calculating our CXY0, as you can see the thing. So, you will be putting A0 plus A1, which is nothing but 1 by 4 CXY0 plus CXY2. So, these are the values what we have it, and then plus 1 by 4 CXY1 plus CXY3. Here we have these are the values what we have it, 7.5 plus 0.5 and then plus 1 by 4 into 0.5 plus j 1.5. So, plus 0.5 minus j 1.5 for the second sequence. So, which you can see that we are getting it as 2.25. So, how we calculated the circular convolution using a DFT property. So, we can calculate these values. So, the next one is CXY of 1. So, you will be substituting these values and then calculate the thing. So, you will be getting it as 1 in this case, same with respect to the next two. So, you will be seeing that the DFT using DFT, the circular correlation values resemble as that of the direct circular correlation what we have calculated. So, coming to the next topic, we have to introduce little on random process. So, we know that real world signals such as speech, music and noise are time varying, and we know that they are random in nature. The set of all possible outcomes in any given experiment is called a sample space S. Why do we need random process? So, you are seeing that some of the applications what we will be seeing later on based on some of the speech and music, already we have seen the thing, how a noise is introduced in the music or in the speech, how we were able to eliminate our noise if our known noise is known in this case. In some of the cases noise may not be known. Okay. So, we have to adapt to the situation, so which requires our random process. So, the next topic we will be covering is adaptive filter. So, we need this basic knowledge of random process, only little bit of it whatever required for deriving our LMS algorithm will be covering it in this course. So, those who want to have more, they can take up it as a course and then complete it. So, this is the space or sample space what we have defined, and we have to define the random variable x. How we are going to define it? This is a function that maps all elements from sample space S into the points on the real line. As an example, considering the outcome of our rolling fair die. Okay. So, we have obtained the discrete random variable that can be any one of the discrete values from 1 through 6. All of us know that our fair die has 6 values. It when we roll it, so we do not know what is the outcome, but it should lie be 1 through 6. So, the cumulative probability distribution function, we call it as CDF, of a random variable x is defined as that basically you can see that there is a repetition here, that is f of x is equal to probability of x less than or equal to capital X, okay, where capital X is real number and p x less than or equal to x is the probability of x less than or equal to capital X. So, we call it as probability density function of a random variable x is going to be defined with that. F of x is nothing but d by dx of f of x, okay, if the derivative exists. So, two important properties of probability density function is f of x are summarized as this way, that is integration minus infinity to infinity f of x dx is equal to 1, and probability of x1 lies small x lies in x1 and x2 is given by our f of x2 minus f of x1. So, which is nothing but we will be putting x1 to x2 f of x dx. So, if x is a discrete random variable that can be any one of this discrete xi, that is I is equal to 1, 2 etc. As the result of an experiment, we define the discrete probability function as pi is equal to the p capital P of x equal to xi, it belongs to this. Okay. As an example, so we consider a random variable small x that has the following probability density function: f of x is equal to 0 in this range, x less than x1 or x small x greater than x2, and in the region x1 to x2 which is equal to a. Okay. So, that is we say it is uniformly distributed between x1 and x2, and constant value a can be computed as with this equation, that is minus infinity to infinity f of x into dx, which is equal to x1 to x2 what we are putting the thing, a into d of x, which is nothing but a into when we expand our integration, which is going to be with the values, it is going to be a times x2 minus x1, which is equal to 1. As this can be seen that, so the maximum value is 1 by x2 minus x1, and then we will be seeing that this is uniformly distributed between x1 and then x2. So, A in this case is equal to 1 by x2 minus x1 what it has been taken. So, that is the reason why we will be getting it as 1 here. So, what is it? If a random variable x is equally likely to be any value between two limits x1 and x2 and cannot assume any value outside that range, it is uniformly distributed in the range that is x1 to x2. So, that is as shown in the figure, it is uniformly distributed in this region. Then we call that is uniform density function is defined by this f of x is equal to 1 by x2 minus x1 in x is in the range x1 to x2, otherwise it is going to be 0 in the other places. So, coming with some of the operations of random variables. So, the statistics what we call it as, one is the first is the mean what we will be defining it, that is nothing but expected value of x which is given by integration minus infinity to infinity x into f of x into dx. So, this is for the continuous time case is defined as this. For the discrete time case it is a sigma xi pi, I is varying. Okay. So, we represent E dot denotes the expectation operation or ensemble averaging basically. The mean mx defines the level about which the random process x is fluctuates or fluctuating. So, you will be seeing that is linear operation. The useful properties of the expectation operation are expected value of alpha is equal to alpha and expected value of A times alpha will be A into expected of x basically, where alpha is a constant what we assume it. If expected value of x is equal to 0, x we call it as 0 mean random variable. So, you will be using a MATLAB function if you see the thing. The mean calculation is given mx is equal to mean of x, computes the mean mx of all the elements in the vector x using the MATLAB function. So, as an example, so we said that our fair die rolling of a fair die. So, we said n times, that is n can be up to infinity. So, the what will be the probability of outcome from this? So, you will be seeing that x is we are taking 6 and then our probability is 1 by 6 in all the cases. And in this case mean is calculated as mx is pi into xi. So, 1 by 6 of this which is going to be 3.5, and the variance the measure of spread about the mean and is defined as sigma x squared, which is equal to expected value of x minus mx whole squared. So, which is by substituting our expected value minus infinity to infinity x minus mx whole squared into f of x into dx for the continuous time case, and it is going to be sigma pi xi minus mx whole squared for the discrete time case. So, these are the mean and then variance what we will be defining it. X minus mx is the deviation of x from the mean value mx. The positive square root of the variance is called the standard deviation sigma x, and MATLAB this thing function for the standard deviation calculation uses STD function. Okay. The variance defined can be expressed as, that is sigma x squared is equal to expected value of x minus x whole squared. So, which is nothing but expected value of x squared minus 2mx in plus mx squared. So, you are taking the expected value inside, which is nothing but expected value of x squared minus 2 into mx into expected value of x, and this is away from our x plus mx squared. So, this is the value what we will be getting at, that is this becomes 0. So, it will be expected value of x square plus mx squared. So, we call this is the mean square value of x. So, variance is the difference between the mean square value and the square root of the mean value. So, this is the random variable definition, some of it what we will be seeing it. So, we see that if what is it mean value is equal to 0, that is mx is equal to 0, then what happens to sigma x squared is nothing but expected value of x squared. So, which we call it as px, which is the power of x basically. Consider the uniform density function. The mean of the function can be computed by this mx is equal to expected value of x, which is nothing but minus infinity to infinity x into f of x dx. So, we have seen the uniform which is substituted at 1 by x2 minus x1. So, your integration x1 to x2 x of dx, which is nothing but x2 minus x1 divided by 2, what will be resulting in. So, variance of the function is defined sigma x squared is equal to this is what we had it, expected value of x squared minus x squared. So, if we substitute the thing with expected value of x squared with that, and then by simplifying, so we will be getting it as mx squared. So, in general, if x is the random variable uniformly distributed in the interval minus delta and delta, so then we will be having mx mean is equal to 0, and then standard deviation x squared is given by delta squared by 3. By substituting in this, you can calculate with minus delta and delta. Substituting it here, you will be getting delta squared by 3 as the value. So, this completes our on correlation and little bit on random process. In the next class, we will be taking it up adaptive filter. So, how we are going to derive it. Thank you.